My name is Shwetha Rajaram, and today I'll be discussing our research on eliciting security and privacy-informed sharing techniques for multi-user augmented reality. This is work done with Chen, Professor Roesner at the University of Washington, and my advisor, Michael Nebeling at the University of Michigan. We can observe a trend that collaborative AR systems are becoming increasingly prevalent, especially in educational and workplace contexts. This raises a unique set of security and privacy threats. Consider this hybrid education scenario, where two students are working on an AR engineering lab in a classroom, and another student is working remotely from his personal home. To enable the students to communicate and collaborate effectively, the AR system should support multimodal interaction techniques like gestures, gaze, and voice. Perhaps the students need to capture areas of the environment to convey how they're working with the physical engine and tools. But these interaction techniques could raise a variety of security and privacy concerns for this scenario, especially involving access control of the physical and virtual spaces. The remote student might want to minimize the information that his collaborators can learn about his physical surroundings, like that he has private mail on the table or that he's taking care of his daughter. If collaboration across lab groups is prohibited, the students may prefer more discrete interaction techniques that disclose less detail about what they're working on. So in this work, we explored how to design multi-user AR interaction techniques with the security and privacy mindset. If we wanted to design and develop an AR system for this educational scenario, there's a rich body of HCI research on multi-user AR systems for us to draw on. To enable ad hoc collaborative AR systems, prior work has addressed technical challenges in environmental sensing to develop interaction techniques utilizing spatial capture and 3D reconstruction, 360 video, and object and people tracking. Recent systems also optimize interaction techniques for important usability metrics for collaboration, such as social presence and task performance for physical tasks. But in our review, we observed a lack of multi-user AR systems designed with explicit consideration of security and privacy goals. We found just a few exceptions that consider viewing access to private AR content. The security and privacy community has been studying ways to address novel threats in multi-user AR scenarios, such as threats involving access control, ownership of physical and virtual spaces, and bystander privacy. But there is still an open challenge of how to bring these security and privacy best practices to AR developers and bridge the gap between these two separate research streams. So as a step in this direction to address potential threats in the earliest stages of AR design, we explored how user-driven elicitation can be extended to incorporate security and privacy considerations. Elicitation is a primary HCI method for designing interaction techniques and has been applied to a variety of AR use cases in prior work. Typically, end users are paired together and presented with a system effect, and then asked to produce interaction proposals to accomplish that effect. To better consider the technical feasibility of interaction proposals, we worked with experts in AR development rather than with end users. To address security and privacy goals in the elicitation process, we extended the production, priming, and partners approach in 3 ways. First, we adopted a scenario-based elicitation approach to provide a concrete basis for analyzing threats. We defined design dimensions to guide the development of the scenario that we introduced earlier, including the time-space matrix and a threat model for access control in multi-user AR from prior work. We created a digital sketch of the scenario, selecting story and visual elements to provide coverage of the design dimensions. Second, we crafted a set of elicitation prompts that increasingly consider threats involving access control by drawing attention to the co-located AR users, then the remote AR users, and lastly, the bystanders and the non-users. And third, we assigned roles of designer and critic within the pairs of participants. We specifically invoked one partner to produce interaction proposals and invoked the other partner to suggest improvements, referring to a handout of the design dimensions. Given these extensions to traditional elicitation, we designed a study with 2 goals in mind. First, holistically consider design goals related to usability, technical feasibility, and security and privacy. And second, assess whether a scenario-based elicitation approach provides sufficient guidance for AR developers alone to mitigate threats in interaction proposals, or whether additional expertise in security and privacy is still required. To accomplish this, we conducted a between-subject study with two conditions, pairing two AR development experts and pairing an AR expert with a security and privacy expert. We studied with individuals who have at least 2 first-authored publications or 2 years of experience with industrial research in related fields. Due to our between-subject design, we recruited 12 AR experts and 4 security and privacy experts. The core of the study was Task 1, where one expert produced 3 interaction proposals to share AR content, and the other expert critiqued with respect to the provided design dimensions. In the AR-AR condition, the experts took turns in the design and critique roles for each prompt. In the AR-SP condition, the AR expert always designed, and we specifically invoked the security and privacy expert to critique with respect to the threat model. We also incorporated a holistic ranking task, where the experts weighed the pros and cons of the sharing techniques based on the 3 overarching design goals. To determine the experts' underlying motivations in proposing techniques and how interaction proposals evolved throughout the study, we created timeline visualizations to plot the design considerations that the experts mentioned for each elicitation prompt. Overall, we elicited 73 total proposals for sharing techniques from pairs in both conditions. Here we show the common classes of sharing techniques, mapped from most popular to most distinct from left to right. Familiar WIMP-style AR menus were the most frequently proposed, while post-WIMP and AR-specific modalities like gestures, proximity-based interactions, gaze, and voice were also popular. The most distinct techniques involved physical tokens and physical interfaces. To address potential threats, the experts produced 65 additional techniques for access control, which frequently were added on to their existing sharing technique modalities. I will walk through a few examples of the more popular versus more creative interaction techniques for access control. Virtual menus were commonly extended with additional access control techniques for user authentication, notifications, role management, and notice and consent. The experts often propose these WIMP-style interfaces since they're standardized techniques for access control in 2D form factors. However, they anticipated usability challenges due to limitations with pointing accuracy and field of view on AR head-mounted displays. To allow for more granular control with proximity-based sharing techniques, experts proposed coarse-grained virtual objects, which maintain the confidentiality of AR content, and inclusion or exclusion boundaries to specify areas of the physical environment that AR devices are allowed to capture. Some of the most creative and distinct proposals included using silent speech to minimize the information disclosed through voice interaction, and sharing a depth view instead of camera data to provide a coarser-grained, diminished representation and protect bystanders' privacy. Comparing both conditions through a timeline analysis, we found that access control techniques were proposed earlier on in the AR-SP condition. However, we observed no major differences in the type of sharing and access control techniques, which suggests that our scenario-based elicitation approach provides sufficient structure and cues for the AR experts alone to design more thoughtfully. While some security and privacy experts were concerned that their critiques would limit the AR experts' creativity, we did not find this to be the case. Pairs in both conditions produced similar quantities of familiar WIMP-style techniques and more distinct AR-specific techniques. We also observed 2 different design strategies utilized by AR experts in both conditions. A usability-first strategy where experts first optimized for usability and made their techniques increasingly multimodal to provide access control, and a security and privacy-first design strategy where experts discarded techniques early on that they perceived to have security weaknesses or be privacy invasive. Based on the expert suggestions, we do recommend the AR-SP pairing for our elicitation approach whenever possible. But when it's not possible to work directly with security and privacy professionals, our scenario-based elicitation approach provides one example of how we can still achieve creative, yet security and privacy-informed interaction proposals. To recap the key steps to take, first, create a scenario visualization with elicitation prompts that consider both AR users and non-users. Second, assign roles of designer and critic to the partners and facilitate turn-taking between them. And third, choose an appropriate threat model for the usage scenario. Thanks for watching our presentation, and please refer to our paper for more details.